Okay, let's go ahead and get started. Welcome everybody to the March Science and Engineering Council meeting. Looking forward to today's discussion. I just want to let everybody know we're here on the this time of the month, second Wednesday, excuse me, and have great topics again this month. Thanks everybody for their renewals and also for sponsorships, always much appreciated. And if, as always, if you want to learn more about us, you can put your name in the chat. We'll reach out to you, or just send us a note. You can reach out to Cheryl or any one of the board members here today. Apologize I couldn't be there in person. With that said, I think we'll go ahead and I'll just turn right back over to Yvonne to talk about some upcoming meetings and then get us started on today's discussion.
Thanks, Tim. I just wanted to point out that subtitles are available in this Zoom session if you choose show captions or show transcript or whatever Zoom is calling it in your installation of Zoom. And records of many of our past meetings are available on our YouTube channel, and I believe we're recording today's meeting, and this will also go up. Today we have a special short presentation from Len Smallboard, who is the programs officer. Interesting. Because I needed it. Okay. He's the chief programs officer of the Scholarship Foundation of Santa Barbara. This is the main charity that the Science and Engineering Council supports, and we typically fund 2 scholarships for STEM majors with financial need each year. And Len's going to speak, and then I'm going to post the donation link in the Zoom chat. Okay. So Len, go ahead. Thank you, Barb. Do you want to stop that share? So that would be a presentation as well. There you go. Right.
It's a pleasure to be here with you this afternoon. Thank you for your ongoing partnership. Because of your work, we're able to award 2 scholarships each year to the Science and Engineering Council here in Santa Barbara to students in financial need who are majoring in one of the STEM fields. So we're just really excited. I'll tell you a little bit about the Scholarship Foundation, some high-level information, 5 to 10 minutes, and then we could follow up with quick questions via Yvonne, or you could catch me. There's some handouts via email or phone call. So I'll just jump right in. So the mission of the Scholarship Foundation of Santa Barbara is to inspire, encourage, and support Santa Barbara County students to and through college, graduate, and vocational school by providing information, advising, and scholarships. Every student in Santa Barbara County or high school student in Santa Barbara County is eligible for 5 years of undergraduate scholarships at a Title IV approved college, which is about 4,500 of them around the world, plus an additional 4 years of graduate school, medical school, dental school, law school. So if they do it right, we're talking about 9 years worth of scholarships for our local students here in the county. Just a little bit of high level information. We've been around since 1962. We've awarded $150 million to more than 60,000 local students. Last year alone, last May, we awarded $7.2 million to 1,864 students at 300 different colleges around the world. So that's, it could be Allen Hancock up in Santa Maria. It could be Sisu Channel Islands. It could be Brixton. It could be a college in New Zealand. As long as it's a Title IV approved college, we are awarding students, which is really exciting for me to share. That means our students are accessing their post-secondary education on a global scale. So a student from Dos Pueblos, a student from Santa Barbara High School, from Santa Maria High School, they can go to school anywhere around the world. And we are here side by side with them, supporting them, helping them pay their way through. So our impact, on average, award for our graduate students. So that's maybe an MBA, that could be a PhD level student, it could be a law student. It's about just north of $6,000. Our average award for undergrads is just a little over $3,300. 53% of our students are first generation college students. That means they're the first in their family to attend any kind of post-secondary education. So they're paving the way for their little brothers, their little sisters, cousins, you name it, for future generations, right? So we all know how valuable post-secondary education is, specifically now with the STEM, specifically the focus of this group. there's more and more need for highly trained, highly educated individuals. Like I mentioned, students are at 300 different colleges around the world, and 28% of our students, based on the federal formula that we use for the FAFSA, their families who contribute zero, which is nothing to their post-secondary education. So based on their assets and income, there's nothing left at the end of the year to send a check to UCSB or Ellen Hancock or Cal Poly, right? So all their resources are going to cost of living. So based on the formula, almost a third of our recipients last year, that's the financial situation of the family. What we do is scholarships. It's in our name. We are also help students with completing their federal and California DREAM Act applications. So just to give you an example, over the last 4 years, the Scholarship Foundation awarded just north of $30 million in those 4 award cycles, but we help students leverage an additional $175 million in federal, state, and institutional aid. So we work with more than 20,000 students and their families throughout the county. So Guadalupe all the way down to Carpinteria, making sure that they're accessing financial resources for their post-secondary education. Financial aid and college access presentations. We have office hours at 31 different schools throughout the county, financial aid workshops, either one-on-one or in front of a large auditorium. We have a team of 4 full-time program advisors who will sit down with the family and help them negotiate their financial aid package, fill out the right forms. It could be a pretty highly bureaucratic process, and we help them navigate pay for school. Summer programming, we partner with more than 90 different nonprofit organizations throughout the county. So Girls Inc., Boys and Girls Clubs, United Way, making sure that they have that information so they know what the cost of college is, but also what is the difference between a community college, a CSU, a UC, or a private institution. So we want to make sure they're making an informed decision. They're planning accordingly for their education after high school. Drop-ins at all the high schools, like I mentioned, and financial aid literacy. So it's something as simple as, when a student has a gap in their financial need, they're often offered a loan. So what's the difference between a subsidized and an unsubsidized loan? Right? We want to make sure that families are making informed decisions around financing of their education. Why we do it? The rising college costs. So there's $1.7 trillion in college debt, student loan debt, and rising. The CUCs are going to be raising their costs by a total of 30% over the next 5 years. So if you are a middle-class family and your kid got into Cal Poly, which is a great state school, it's about $35,000 to $36,000 per year. So you're paying almost more than $120,000 over 4 years if your kid graduates in 4 years from Cal Poly, just for their undergrad degree, if you're not getting any additional aid. So the numbers are getting really, if you got multiple kids, and we're lucky here in this county because we have the Promise program of SBCC, right? First 2 years are completely free. And now the Ellen Hancock Promise program, first 2 years are free up in Santa Maria. But once you get into the 4-year institutions, the prices go up if your family does not, if you're a lower or middle class family does not qualify for any financial aid, you're paying full price. So that's why we do it. We want to make sure that data shows that students who have financial support complete post-secondary education at a higher rate. We want to make sure that if we know that they graduate, they get their jobs that they receive are more sustainable. They pay more taxes, they volunteer, they're more involved in their community versus if they're working multiple jobs just to scrape by. How we do it? Generous donor support, like the Science and Engineering Council here in Santa Barbara. Your 2 scholarships go a long way every year for 2 students. Community volunteers. We have a board of about 30 individuals who constantly and tirelessly champion our cause. We have a team that's highly trained. So the federal financial aid forms were a total revamp going into this fall. So we went to 12 different trainings sponsored by the federal government, making sure that we are able to answer students and their families' questions here on the local level when it comes to accessing additional aid for college. And then strategic community partnerships. As I mentioned, we work with more than 90 different organizations throughout Santa Barbara County. Ways to support. So continue to support the Science and Engineering Council Scholarship Program. Well, your generosity is acknowledged and it's deeply appreciated. If you're interested in starting your own scholarship, every scholarship dollar that you put into the Scholarship Foundation, 100% of it goes to the student directly to pay for their education. There's no fees on top of that to process or administer that scholarship. So if you want to celebrate a family member, a friend, your alma mater or local student who might be attending your alma mater or is interested in attending your alma mater, students studying specific field or pursue a specific career. So we manage the best way to look at the Scholarship Foundation of Santa Barbara. We're a clearinghouse for more than 500 different scholarship funds. So there's a fund for an engineering student at Cal Poly who's also on the bowling team. Yes, that really exists, your scholarship specifically for your STEM folks, 4-year university with financial need. So there's ways to tailor your scholarship to meet your goals or your organization's goals that we work with, like I mentioned, more than 500 different funds. Or, we also have alumni of local high schools say, you know what, I want to fund a high school senior who has a 3.5 GPA or above, graduate from those programs. So we work with those schools directly. That's nice to support the organization. Overall, we're seeing an uptick in need. Last year, we turned away 1,400 eligible students who would have received funding if we had enough funding. Throughout Santa Barbara County, our high school seniors are graduating at more than 90% rate, which is great. And 70% of our high school graduates are going on to some kind of post-secondary education. So they're accessing post-secondary education training, but now they need the resources to be able to pay for those courses or degrees. So that way they are not graduating with a ton of student loan debt, would really impact their ability to start a family, buy a home, invest in a business, so on and so forth. I think that was 5 to 10 minutes. Yvonne, it's your call. I can take questions. I can pack up. It's totally up to you guys.
Anyone have quick questions? You can unmute yourself or somebody in the room. Okay, I've posted in the chat. Joseph, can you go get that? The link for donating. When you use this link, be sure to say that you want your scholarship to go to the Science and Engineering Council Fund on the page. So that's it. Great. Thank you so much.
Thank you, everyone.
Thank you. Thank you. Okay. And now, give you an idea of our upcoming topics. We'll be letting you know soon about the topic of our next meeting, which will be on April 10th. On May 8th, Dr. Prajakta Kulkarni will be speaking on AI for disease prediction and early detection, opportunities and challenges. I'm looking forward to that talk. She's the founder of SkyCare, kidney health company. As always, feel free to contact me about particular topics or speakers you would like to suggest for upcoming meetings. And as far as events held by other groups around town, we're trying to announce those, and they are announcing our talks in return mostly. Tomorrow evening, which is Pi Day, the Los Cumbres Observatory is hosting Astronomy on Tap at M Special Brewing in Santa Barbara. And the featured topic is ethanol in ether. And on March 19th, the Kavli Institute for Theoretical Physics is hosting KITP, Cafe KITP at Soho Restaurant. And their topic is Stellar Sleuthing, How Scientists Learn from Lights in the Sky. And then on March 20th, the Ventec meeting is on raising money in hard times. And our speaker today is Dr. Benjamin Carlson. He's an assistant professor of physics at Westmont College. Dr. Carlson works on the LHC's Atlas experiment, which is the largest detector ever constructed for a particle collider. He works with undergraduate students in a unique program supported by the NSF. In particular, he looks for hints of new particles in decays of the Higgs boson. Dr. Carlson also works on the Atlas trigger system, which determines which collisions should be saved within a fraction of a second. He received his PhD in physics from Carnegie Mellon University and was the Samuel Langley postdoctoral scholar at the University of Pittsburgh before coming to Westmont. So he's speaking to us today on Beyond the Hidden Higgs Boson. Welcome, Dr. Carlson. Thank you very much.
Yeah, so thanks so much for having me today. I have been able to come to some of these, at least one other meeting in the past, and really enjoyed it. So thanks for the opportunity to talk to you. Yeah, so I'm going to talk about my work with the Atlas experiment, which is the LHC. I'll tell you a little bit about that. And I'm a professor at Westmont College, so it's a little unusual to have a group at one of these experiments at a small college. So I'll be telling you about what it's like to work with undergraduate students. And if you want to know more about our program, our physics degree, for instance, you could ask me. I can tell you more about what it's like to study physics at Westmont. So let me start with some big picture kind of goals of high energy. So it's a little abstract. So let's start with a picture that you might be more familiar with. You've probably all seen articles about the James Webb Deep Field, and most of us probably have enjoyed looking at images from astronomy, right? In a way, particle physics is doing the same kind of thing. Instead of looking out at very large scales to understand fundamentals about the universe, we're building better and better microscopes, or at least analogy to microscopes, to look the other direction, to look at things that are really small. And in terms of the range of distance scales, they're relatively similar. On the left-hand side, you can see a bunch of different distance scales, starting with 1 meter, which is roughly our size. And in particle physics, what we're trying to do is push below the size of an atom into the nucleus, and smaller fundamental particles, and even beyond, to understand the most fundamental laws of why we live in the world that we do. So particle physics is about fundamental questions. What is the universe made of, or what are the building blocks? We call these elementary particles. So most of us are familiar with one of them, it's the electron. In circuits, you have electrons, right? We're also interested in what holds the pieces together. What are the forces? So for instance, the electron is attracted to a proton, which has positive charge. That's an electromagnetic force between them. And I'll tell you how a particle physicist thinks about that a little bit later. It has a quantum mechanical nature, it's a relativistic nature, but we're interested in what are the pieces and then how they hold together. Now, we're also interested in building experiments. We use technology that I think is really exciting and interesting, but the main purpose of everything that we're doing in the kind of work in high energy particle physics is because we want to get at these basic questions. Now, again, coming back to this diagram on the right-hand side, we want to start to probe to smaller and smaller distance scales. So how do we do that? Let's start with a little modern physics. This would be in, say, a sophomore physics class, and probably most people are familiar with this. The wavelength of every particle, according to Boson, is the Planck's constant over the momentum. So if you want to look at something small, it means you need to go to a very small wavelength, which means that the momentum has to go up. So how do you do that? You take some particle and you increase its momentum higher and higher, and then you can start to look at things that are smaller and smaller distance scales. Usually we think of not just the momentum of the particle, we might interchange that with its energy. So you might hear particle physics called high energy physics. So go to a really large collider, go to very high energy, for the particles that are being collided. We're looking at things that are very small, therefore allow us to start to explore the fundamental nature. Now, I also want to tell you about an experiment that, again, I think most people are familiar with if you had a high school chemistry or physics class, potentially. And this is sort of the prototype particle physics experiment. And it's over 100 years old, but it's just a fantastic way to think about looking for things that are small. So 1909, Rutherford, Marsden, and Geiger, they build this classic experiment. They take an alpha particle and they then allow it to pass through a thin foil of gold with a particle detector made out of some phosphorescent material. And the reason that they did this is because they wanted to understand something about the atom. In particular, they want to understand if the atom has the charge evenly distributed through the atom. We know that the atom is neutral, but we also know that it has positive and negative charges in it, right? So at the time, it was thought the charge was evenly distributed around the atom, and therefore, if you construct this experiment with alpha particles which are charged, nucleus of helium, that on average, there'll be not too much deflection because as they start to see the charge in the nucleus, it will bounce off many of those charges. And so in this video, you see lots of alpha particles going through the nucleus, and very little deflection. That's called the Thomson model, or maybe you heard of it as the plum pudding model. On the other hand, if you zoom in and say, instead of the charge being distributed around the whole atom, maybe it's at a very small nucleus which is inside the atom. Zoom into what turns out to be the equivalent of a few pixels and create a different model. What instead you see is these charged particles coming in, getting very close to the charge at the center of the nucleus and having very large deflection angles. What that means is that if this model is correct, where the charge is at the center of the atom, the deflection angle will be very large for some of those alpha particles. It turns out the second model is the right one, as I'm sure most of us know. There's a very small nucleus at the center of an atom. And the way that you arrive at that conclusion is by looking at essentially a histogram of all of those scattering events in that picture of the phosphorescent screen. You look for some events that have large scattering angle, close to 180 degrees. What that means is that in that picture, they're bouncing back towards the source. When that happens, you get these large scattering events because there's a charge at the center of the atom instead of being evenly distributed. Turns out you can also predict the distribution, and it goes like 1 over this equation, 1 over sine to the 4th. And this is a totally different prediction than what you would get if the charge was evenly distributed. Rutherford says this is the most incredible event in his life, and it compares it to what happens if you fired a cannonball at a piece of tissue paper and it bounces back at you. So that's kind of the prototype of a particle physics experiment. I'll tell you about some experiments at much, much higher energy than the energy of an alpha particle. But the basic concept is the same. You're doing a scattering experiment. You construct a histogram, quite like this one, to look for some knowledge of what's happening inside the scattering particle. By the way, the prediction for this Rutherford scattering model is so far off of what you get for this Thomson model that as soon as you see a couple of events here, you know that there must be a nucleus. So that's some history, but I think it's a really helpful way to think about art. There's more that we need to take into account, though. So we need to take into account Einstein. For instance, the mass is related to the energy and the momentum. This might not be the equation that you're used to thinking of when you think of Einstein. Maybe you think of mc squared. Turns out it's the same thing. But this equation tells you that the mass is related to its energy and momentum. And if you take that equation and combine it with quantum mechanics, then you actually predict a whole additional set of particles. For instance, Dirac predicted that there should be a partner to the electron, which has positive charge. It's called the positron, or the antiparticle for the electron. And not too long after Dirac predicts this, using relativity and quantum mechanics, it was discovered that you could use cosmic rays, which come from outer space, and you could construct a basic particle detector called a cloud chamber. And you could see particles that have the same properties as the electron, but the opposite charge. And that confirms that this prediction from Dirac is correct. And so there's 2 Nobel Prizes that are worth noting here. One is for Dirac and Schrödinger for predictions from quantum mechanics, essentially, and then another one from cosmic rays and the discovery of the positron. So just recapping some essentially 100-year-old modern physics, we have the wavelength being inversely proportional to the momentum. So small things mean high momentum. Second, the Rutherford scattering example, discovering the nucleus, and then combining quantum mechanics and relativity. Those are essentially the building blocks of particle physics. And so you might think of it in this picture. We start to construct a picture of an atom where there's a small proton at the center. The electron is very far away. For a hydrogen atom, this turns out to be about 5 orders of magnitude, which is really an immense distance scale. I like to think of it as like the electron is about this size and the proton is in Santa Barbara, roughly speaking. Now, it turns out that that same type of experiment, same type of scattering experiment with the alpha particles, you can repeat that, but now for the proton, which is inside the atom. And those types of experiments were done roughly 1960s and 1970s. And they tell you that not only does the proton sit at a very small part of the atom, but actually the proton itself is made up of other particles. You can break the proton apart, and there are these particles that come out of it called quarks. They're held together by some interaction that's different than the electromagnetic interaction, which holds the electron to the proton. So there's even more structure when you start to break apart the proton. So let me recap this in terms of the language of elementary particles. We talked about some of the building blocks in terms of atomic physics and nuclear physics. These are called elementary particles, but we don't want to stop there. We want to ask if there's other undiscovered particles, and there's a very good reason to think that there might be, and that is dark matter. I'll tell you what it is and tell you how we might look for it from a particle physicist perspective. And then the same question in terms of the interactions. What are the forces? And are there other new forces? And then how does the Higgs boson interact with both of these different issues? So that's an introduction, and let me give you the outline for what I'm going to tell you today. So I'm going to tell you a little bit about the formalism or summarizing all of the different particle physics observations we have. It's called the Standard Model. Then I'll tell you about tools, in particular, the Large Hadron Collider and the ATLAS experiment, some of my specific work, and some of the challenges for the future. So this picture of taking the proton and starting to break it up into constituents. Those constituents are called quarks, but it turns out that they're held together by a strong interaction, and electromagnetism also can interact at very high energies, can have another a weak interaction, and there's a whole lot more than what I've talked about. And you could describe it in this mathematical language called the Standard Model, which essentially encapsulates all we know about particle physics using quantum mechanics and relativity. The equation is not worth going into, but just to show you the complexity, it's on the right-hand side. This is an easier way to think about it. Here's a picture, kind of like a periodic table, although that's a little of an oversimplification. But let me walk through a few key features. So spin of the particle, which is its intrinsic angular momentum, plays a major role. All of the left-hand particles are spin 1/2 particles. The proton is made up of spin ups and spin downs. The electron is a fundamental particle. But there's also these copies of those particles that are heavier. So there's a copy, for instance, of the up quark called the top quark, but it's much heavier. That's a really important. That's why I mention it. The interactions, on the other hand, all have to do with these spin 1 particles. The photon is one that mediates a familiar electromagnetism. So for instance, if there's a particle with an electric charge, like the electron, then that interaction is mediated by the photon. Similarly, the strong interaction is mediated by the gluon. That's what would hold together, say, the quarks inside the proton, to form a bound state. The proton is bound state. And then there's some copies of the photon, one of which is neutral but massive, called the Z boson. The other one is charged and massive, called the W boson. And you might have heard these as being responsible for radioactive decay. But in many ways, it's easier to think of these as being somehow related to the photon. Now, one mystery, if you stop there, is that these particles have mass. What that means is they don't travel at the speed of light. In the Standard Model, there's a mechanism for the origin of mass, and that's called the Higgs boson. It is a spontaneously broken symmetry. So there's a symmetry that's related to this particle called the Higgs boson that is broken in a way that gives mass to all of the other particles in the Standard Model. It turns out it's also the hardest particle to see in an experiment, and it was only discovered about 10 years ago at the Large Hadron Collider. Discovered in 2012, and then there was a Nobel Prize announced for this particle in 2013, given to the theorists that came up with the mechanism. And the ATLAS and CMS experiments, which discovered the particle, were also mentioned in this prize. So this is a very significant and relatively recent discovery, and a very important kind of achievement for the Standard Model. So it turns out that despite describing all of the particle physics experiments that we have been able to do, there are some open questions that have not been addressed or need to be addressed. And so I'm going to talk about a few of them, but if you go through the problems in modern physics, there are many. One of them is called dark matter, and it turns out this is about 85% of all of the matter in the universe. That one I'll spend some time on. There's also issues with the mass of the Higgs boson. Theoretically, it's called the hierarchy problem. And there's some other theoretical issues with the standard model. So we don't really think our job is done. We think that there's a lot more going on, and there's some interesting and important areas that can still be explored. So let me tell you a little bit about why, one of the best reasons I think for why we think there's other physics out there. This is called dark matter, and it's been known for some time. We know that if we look in astrophysics experiments and we say, take all of the stars around a cluster or a galaxy and plot their rotational velocity as this function of the distance from the galaxy, what we expect is the red line. What we see is the white line. That tells you that there's additional mass that we can't see. It's mass that's not accounted for by stars, for example. And we know it from many ways beyond rotational velocity curves. We know it from gravitational lensing experiments, where space-time is curved. We know it from at least half a dozen other examples. So we know that there's something else out there that we're not seeing in stars. And it turns out that that is not explained by the standard model. There isn't a particle that can account for enough mass that could account for this. And there's also this issue of dark energy, which has to do with the expansion of the universe. I won't go into that, but dark matter, I will talk about, and that is a pressing question for a particle physicist, and one that we want to be able to address. So if you just take the standard model and atoms in the universe, we actually understand a pretty small piece of it. So there's a big scope for what we want to do in the future. There's some theoretical reasons as well for issues with the Higgs boson that we want to address. I'm going to focus on the second piece, though, which is that there's some possibility that the Higgs boson might be a sort of connection between dark matter and the standard model. And so that's an area that is relatively well motivated theoretically. It could sort of solve some of these problems, both the dark matter problem and some of the theoretical issues, and bring them together into one unique signature that we might find in the decays of the Higgs boson. I'll just pause for a minute and see if you have questions you want to address now. I'm also happy to talk more at the end, but if there's any questions you want to ask. Okay. So let me tell you about the Large Hadron Collider at the LHC and the experiment over. So it may also be worth clarifying that in particle physics, there's a collider, which provides the collisions, and then there's a detector, which measures those collisions. And I am the experimentalist that works on the detector, not the collider. But the collider is obviously very important. So think back to this Rutherford example, right? Alpha particles, there are a couple of MeV, or mega electron volts, and they're colliding against a fixed target. What I'm going to be telling you about is taking beams of particles and bringing them together at a single point and smashing them together. So why do we want to do that? Well, it turns out that the energy, if you can bring two beams together, scales like twice the energy of each of those beams. If instead you had a target like Rutherford did, the center of mass energy, or what you could make in that collision, is proportional to the square root of the beam energy. So just to do a little calculation, let's suppose that the beams are like the LHC beam, and you collide them, you get 14 TeV, or twice the center of mass energy, or twice the beam energy. Whereas if you had a fixed target, you get roughly 2 orders of magnitude lower. So really what you want to do is have a true collider, high energy beams, bring the beams together and collide. And that's essentially a consequence of kinematics. The LHC, as I'll tell you soon, is made of protons. You have proton beams that are collided. And the reason we use protons is essentially that the power radiated by synchrotron radiation, which is radiation due to charged particles accelerating, is inversely proportional to the mass to the power of 4. So if we put an electron in the same ring, which is in fact something that was done before the LHC, then you would have a significant amount more radiation. So if you want to double the energy with electrons, you would need to increase the radius to about 100 kilometers. Also something we want to do. But in terms of the current tunnel that we have at the LHC, protons are the right particle to use. Now, there's a significant issue in what happens in the collisions, which is that if you have electrons, it's a fundamental particle, so there's fundamental interactions that occur. You know exactly how much momentum and energy was flowing into that collision. Whereas with a proton, remember I told you they're made up of quarks, and so you actually don't know how much energy went into a given collision. So a little bit about the history of colliders and how they work. The basic concept is that even in the 1930s, if you watch the movie Oppenheimer, you saw a person who created one of the first accelerators, who was Lorentz, right? So Lorentz has this accelerator where there's an electric field, which accelerates the particle, and then a magnetic field, which causes the particle to be accelerated by that same electric field many times. And we use the same basic process at the Large Hadron Collider, only many orders of magnitude higher in energy. The scale of the y-axis is in essentially proton masses. So a proton has a mass of 1 GeV, or giga electron volt, and the Large Hadron Collider is roughly 13,000, or it's about 13,600 at the moment, but it's about 13,000 masses of protons. So we're increasing the energy substantially. Think back to the picture of fundamentals. That means we're going to smaller and smaller distance scales to be able to populate this picture of fundamental physics. The Large Hadron Collider itself is the highest energy particle collider in the world at the moment. It's in Geneva, Switzerland, and there's a picture showing the farmland where this collider is sitting. At least it's sitting underneath us in a tunnel. The radius, or the diameter, is about 9 kilometers, so it's about 27 kilometers in circumference. And if you were to say bike around this, it would probably take you, a big chunk of the day. There are actually 4 detectors where the particles collide, where the protons collide, and 2 of them I won't discuss, but 2 of them essentially do the same thing and are worth mentioning. One is called the CMS detector. So if you've talked to someone from UCSB, they work on the CMS detector. I work on the Atlas detector, which is on the other side near Geneva. The collider itself is made up primarily in that tunnel. Most of what you would see is dipole magnets inside these long blue sections. And the dipole magnet is what causes the charged particles to bend. And so you could bring it around the ring many, many times. There's about 1,200 of these dipole magnets. They are superconducting, cooled with liquid helium, and there are many of them in the accelerator. In terms of how long it took to build this, I think this time scale is really important and interesting. Remember that the idea was proposed in the 1980s. It was construction or confirmation to start was in the 90s, and then it didn't actually start taking data until 2010. So when I started as a graduate student, it was right around the time when we were first starting to collect data at the Large Hadron. And it's not over. This experiment is going to run for roughly another 20 years, give or take. But if you want to see that, I'll show you later. So what happens in the collisions? Well, protons collide and they break apart in such a way that they create byproducts in a very short amount of time. And our goal as a detector is to measure the outgoing particles. So we need to measure all of the outgoing particles and exactly measure, or as well as we can, measure the energy and momentum. If you took maybe a modern physics class, you might hear that called a 4-vector, because it measures both its energy and momentum, which completely describes the state of the particle, or the kinematic state. So we want to measure all of those pieces so we can reconstruct what happened in the collision. The experiment itself, and I will tell you more about the detector, but it's also made up of many different people. There's about 3,000 authors from 180 different institutions located in about 38 countries. One of the groups on this experiment is Westmont College, which is the group that I have. And these are some of the undergraduate students that I've worked with to collaborate on the Atlas experiment. We're one of the few liberal arts colleges that have the opportunity to work on one of these multi-purpose experiments at CERN. The detector itself is also immensely large and complicated. It's about 150 feet long and it's about 80 feet high. So when you walk into the experimental hall, you really can't see the whole thing. You can only see about a quarter of it, and it's still very impressive. But that doesn't really get to the details of the experiment. This experiment is an immense piece of engineering. There's a magnetic field, which is critical for measuring the momentum of charged particles. And there's about 100 million electronic channels for data readout. Those come from a number of sub-detectors, which build up the overall detector. So from the inside out, there's a silicon detector. The silicon detector allows you to measure the position of where charged particles went, and you can measure many of these charged particles simultaneously. Then there's something called a calorimeter, which can measure the total energy deposited into the detector from both particles that interact electromagnetically and those with nuclear interactions, strong interactions. And then there's a particle on the outside that detects something called a muon, which is like an electron, but heavier. If you want to see it in pictorial form, this is kind of how you think about why we have such a complicated detector. An electron, that's a fundamental particle. We want to measure that particle. So what we do is we have a magnetic field. Again, the magnetic field causes the charged particle to bend. So depending on its momentum, we know the magnetic field, and so we can reconstruct the momentum by how much it bends for the electron. And then we designed a calorimeter which forces the electron to give up all of its energy. And then we measure the total energy deposited in the calorimeter system. The muon is another fundamental particle that's like the electron, but heavier, but it decays eventually. However, because of time dilation, they're so relativistic that for the purposes of this experiment, muons don't decay. And here we do the same sort of thing where we measure the curvature, but we have another detector that's very far away, about 10 meters or so out from the center. And so that allows us to construct 2 points, one at the outside and one at the inside, to measure this momentum. Now, let's say we want to measure the decay product of a quark. Well, a quark is a fundamental particle, but turns out they can't be observed directly. And what happens is they form lots of other particles in a shower. And these particles are reconstructed by using tracks for decay products that we can see that are charged, and then by forcing all of these particles to give up all of their energy in 2 different detectors. And these detectors are literally constructed out of materials like iron, where you have a high energy particle come in, you measure it, you have a layer of iron, it might be a nuclear interaction, you measure it again, have another layer of iron. And so at the end of it, all of the decay products have been measured, or at least sampled. Turns out we can also look for the presence of invisible particles like dark matter or a neutrino. They're invisible in the sense they have no interactions with the detector, and we can see those. And I will show you a picture that I think will explain that better. First, let me show you some pictures of other events. An event is a single snapshot taken with our detector camera. This is one with 2 jets. These jets are quarks or gluons that were very high energy, and they decayed on opposite sides of the detector. This is probably one of the more extreme events that we've seen in our experiment. You can see that there's a lot going on. Inside the center, there's several hundred charged particle tracks. You can see them curving a little bit. That's how we know their momentum. If they're very straight, it means they're very high momentum. So you can see some straight tracks inside the jet. Then there's colored information that is in both calorimeter systems. So the green is something that was electromagnetic. The orange is something that was in the hadronic calorimeter. So maybe it was a pion, which is a bound state of quarks. So you put all of this together and you can start to infer what happened in the collision, even though that collision itself happened for a very short amount of time. This is an event that might be related to a Higgs boson decay. In this particular event, there's an electron on this side, so it's electromagnetic only. And then on this side, there's two jets that are like what I described before. One thing that's interesting here is that there's a straight electron track, so very high momentum, pointing right into the same part of the detector that later saw the energy in the colorimeter system. So I mentioned that we might want to see a neutrino, which is invisible, or dark matter, which doesn't interact with the detector. Invisible means no interactions with the detector. And here you can see on one side of the detector, there was a really high energy jet, which could be from, say, decay of a quark or a gluon. On the other side of the detector, there's nothing. Now, it turns out that can't happen in physics because that would violate one of the most basic principles, which is the conservation of momentum. There's no momentum in the plane that is perpendicular to this beam collision called the transverse plane. So it means that there must be some other particle, it's just that our detector didn't see it. So if we see events that have this kind of asymmetry, it tells us that there was an invisible particle. We don't know what that particle is. It might be a neutrino, it might be a dark matter, but it allows us to come up with a way to identify the kinds of events that we think have this kind of signature in them. So if we want to look for dark matter, you look for events where there's missing transverse momentum, or there's essentially an asymmetry. Look for a jet on the top half and nothing on the bottom. If you're interested in some of the details, we can't use the initial state because the proton is made of quarks, so we don't know the initial momentum. And it turns out we also can't use the longitudinal momentum because we don't totally measure the energy going down the direction of the proton beam collisions. A little bit of a technical point. If you want, I can talk about that after. There's another really interesting complication to these collisions, which is that there's lots of collisions happening at the same time. The way the collider actually works is to fill the ring with bunches of protons and bring the bunches together in one interaction point. And those bunches often lead to many proton collisions on top of each other. You might think of this as multiple interactions simultaneously, or the jargon we use is pileup. And what it results in is pictures that look like this, where there's, say, an interesting interaction, like a Z boson decay, the red lines, and then lots of other stuff sitting on top of it. So we have this challenge of trying to separate out the interesting pieces from all the other noise. If you think, oh, that looks like a good application for AI, sure is. Why do we have multiple interactions? Well, because of the fact that we want to collect a lot of data. We want to collect a lot of data. It means that the delivered luminosity, which is just a measure of how many interactions occurred, that has to go up quickly. And if there's multiple interactions, they are going to overlap in the same collision. It's just one of the realities of collider experiments. So these are very noisy events. Now, partly because they're so noisy, it means we can't save them. We have to throw away the vast majority of our events. And so here's a little sketch of how that looks. Each event we save with some zero suppression, so we remove some of the channels that are not the 100 million channels that don't have anything in them. Turns out that compressed size is about 1 megabyte. Well, the LHC is filled with events that are spaced by 25 nanoseconds in time, which leads to an event rate of about 40 billion collisions per second. And that is an enormous amount of data. It's roughly 40 terabytes per second with that event size. And so you just can't save it all. So what we do is we have what's called a trigger system, where we take some of the data off of the detector in a combination of analog or digital electronics. It's moving more and more to digital electronics, but this system will then process something from the entire detector in about 2 microseconds, so about 2 millionths of a second. And we will decide if we want to keep that particular collision. And then we'll throw away most of the events. So we'll go from 40 million to 100,000. Big reduction in rate. If we like the event, then we say, save this to some hard drives. And these hard drives have to that system, we have about 100 gigabytes going every second. And we have a big computing farm, which has roughly 50,000 CPUs in it. And we can process that data very quickly. And so this one, we have roughly 1 million times longer. We can take about a second to go through each event. And we run algorithms in C++, basically, which is a very optimized computing language for this kind of calculation. And so we do very fast calculations, but something that I can in principle run on my laptop, just that I need a lot of computing to do it. And then this reduces the amount of data by about another 2 orders of magnitude. So at the end, we're saving roughly 1,000 events per second, which corresponds to a data rate of about a gigabit per second or so. So that's the background for the experiment. I don't see the clock. What time is it?
12:54.
Thanks. So let me tell you a few things about some active research that I'm doing on the Higgs boson, particularly looking for invisible dark matter signatures. Now, I want to put this in the context of the discovery of the Higgs boson. So after the discovery of the Higgs boson, it turns out that we're at a sort of interesting point, because now what we want to do is figure out how to solve all these other problems that I mentioned. And so you can kind of do 2 things. You can measure properties of the Higgs boson and look for deviations, or you can kind of propose specific models and look for those models, which I'll call new physics or beyond the standard model physics. And the whole idea is that it's something totally creative and new that is not part of the models that we've had so far. We know it needs to be there, but what specific model is correct is anybody's guess. So it's very exciting. And it also is a very exciting time in the sense that we're still really trying to highlight the secrets of the Higgs boson, and this these different key points, one of which is reveal the secrets of the Higgs boson, came from December, which is part of the P5 report, or the summary, or really consensus of what high energy physicists want to do in the next 10-year period. So I'll tell you a little bit about specific search that I did, which is to look for Higgs bosons decaying to invisible particles, which might be related to dark matter, for instance. Now, just a little bit, actually, I'll skip that. Out of time. So let's start with this Higgs boson plot. This is a plot that shows how events are collected if you were to, say, speed up the collision time. We're collecting more and more data as time goes on. We're looking at a particular variable and then starting to see the Higgs boson come in right here at this particular mass as time goes on, and we collect more data. You can start to see some prediction, or some events come above the prediction, which is shown in red here. And this is the signal that allowed us to say, hey, we found a new particle here, which in that case was the Higgs boson. So the idea is we want to do the same thing, but instead of looking for a particle that is very well predicted, we'll look for something else. And that particular hypothesis is that the Higgs boson has some non-standard model decays to dark matter. And we'll look for that by using this principle of momentum conservation or asymmetric events, and look for some other signatures of the events that are very different than what the background is. This is a particular picture of what we think one of those events would look like. If you just took one of them, it might look like this display here. What we actually do is statistical analyses on many events. Turns out, take one, you actually can't tell what happened. What you can do is look at all of your data and do a statistical analysis, which again is histogram, just like that Rutherford scattering experiment that I showed, and look as a function of a variable that is sensitive to separating signal and background. There's a lot going on here, which I'm not going to go into. I could talk for half an hour about just this one plot, but the main thing is that we expect to see, if there was a signal here, we would expect to see the data events come above the background. And if we don't, it allows us to make a very quantitative statement about that model that we were looking for. In this case, we can make a quantitative statement to say that less than about 14% of Higgs boson are decaying to this dark matter. Is that significant? Well, one way to ask that question is to compare it to other experiments. Now, at the Large Hadron Collider, you make very high energy particles and you collide them and see if you can make some other new particle like dark matter. There's a whole other set of experiments that are also looking for dark matter, where the idea is that dark matter somehow scatters off of a nucleus and you look for the nucleus bouncing or recoiling against the dark matter. I'm not going to go into the details, but with some very strong assumptions, we can compare these. And it turns out that this line here, which comes from this Higgs model, is more sensitive than, for some regions of dark matter, mass is more sensitive than other methods. But just know that that comes with a lot of assumptions and caveats. So it's not the case that universally this is doing better. It's just that for certain assumptions, we are starting to explore things that hadn't been done before in other contexts. Skip these slides. There's a whole lot more we can do with the same type of search. We can look for more specific proposals. If you want to know more about it, I can tell you more. But I do want to tell you just a little bit more about the data collection process, which is continuing. So the results that I talked about in the previous slides were mostly collected through about 2018, which is 5 or 6 years ago, right? So we're taking more data. We're doing it every year, and we took data last summer and the summer before. And we're going to essentially double the previous data set, or even a bit more, than we had at the end of 2018. So I've been involved in that process, and my students at Westmont have also been involved in that. So you can see here a student who's installing some servers that go into that software trigger system. And he's a Westmont student who was there for the summer and taking part in essentially the data collection process that is happening during summers every year. I've also been involved with the same students in working on the algorithms that run in that software system to look for these dark matter events to make sure we can save them. And these are very technical plots, but basically what they mean is we're using more information and we're making better triggers. And even though we've done many things to our detectors, we're still saving those events. What about the future? So I mentioned that the Large Hadron Collider is going to continue for roughly another 20 years or so. So I'm going to tell you a bit about the challenges of the high luminosity LHC, and then how we can use AI or machine learning to address some of those questions. So one of the things that we, broadly speaking, want to do is, coming back to this deviations picture, if we want to measure properties of the Higgs boson very well. We want to do all of the kinds of searches that I talked about where you make a specific proposal and look for them. Those are also very important in the future, but we also want to use a large data set to do very precision measurements. And this particular chart, it shows you a prediction, which is the dashed line, for how the mass of the decay particle, Higgs is decaying to a particle, how that scales, or how its strength essentially scales with its mass. And so some of these we haven't been able to see. One of them is the decay to a particular kind of quark. And I mentioned that one because it's very hard to see at the Large Hadron Collider. I've written a paper about it. Just to give an example of something that we need a large data set to be able to have sensitivity to. We want to have lots of data. We want to understand the Higgs boson very well. Now, I also talked about this problem of pileup, right? So let's imagine this picture on the bottom left. This is a picture from roughly the run 2 data that I think has about 50 collisions in it at the same time. In order to collect the luminosity that we need for the total amount of collisions disk, it means that we need to increase the number of collisions happening at one time. And that means that these events get very busy. So they go from something that looks complicated to something that just looks like a total mess. Each of these purple lines is a different charged particle. That is going to occur over many different periods of running. So for instance, this period I talked about that's happening now is called run 3. We're going to do a big upgrade after that ends, and then prepare for this high luminosity setting for moving forward for the future so we can collect a lot more data. Those upgrades in particular involve everything from, those will happen in roughly 2026, which is the final major upgrade for the LHC. And those will include all kinds of different components of detector upgrade. So in particular, the tracking system, which measures those charged particles, that's going to be totally replaced. Part of that has to do with radiation damage. Part of it has to do with being able to measure better tracks in the high luminosity environment. Muon hardware is going to be upgraded, and the area that I'm working on is the trigger system, which saves events. And just to give an example of why that's important, this plot on the left shows you some examples of, as a function of the number of interactions, just the amount of data of rate, which is number of collisions we think we see per second in our trigger system. And it's basically exponential. So if we did this for the future, it would not work. We wouldn't be able to save all the events. So we have to have better, more sophisticated systems. And so that's my main area of interest. Now, in order to do that, there we go. In order to do that, essentially it means we bring more data into the system. So right now we have about 7,000 individual pieces of data coming in. We are in the process of, in the current run, even to upgrade this to about 36,000, which is roughly a factor of 5. And we're going to increase that to every single piece of detector that we have instrumented, which is going to be about 250,000 individual detector elements coming into our trigger system. So it's a big opportunity. And that comes with lots of upgrades to the hardware. This is a technical chart that shows you how that data from all of these individual pieces of calorimeter flow through the trigger system. And it's also running in custom hardware electronics in that low latency system. So if you want to make a big impact, it's going to be in this system here. One of the things that I've been working on is using AI or machine learning to be able to put those models into these special high-speed electronics chips. And so this is a specific example that I wrote with some co-authors in the last couple of years, but it basically allows me to look for whether or not a Higgs boson was produced in the first place, and then save all of those so we can analyze them later. This particular model uses what's called a boosted decision tree. It has about half a dozen different inputs that allows to separate the signal from the background. I'm also interested in some other techniques in AI that allow us to look for something that wasn't expected. So here the goal is to take something that is not using any particular hypothesis, but just looking for collisions that are very different than everything else. Since I'm out of time, I will allow you to come back to that if you're interested. Finally, I'm in Santa Barbara, so I want to engage students in Santa Barbara and build a strong physics program in Westmont. So one of the things that I've been doing is working with local high schools. So at the moment, one of the programs that's been going consistently is a program with Santa Barbara High, where we have students come to campus. We do some demos in the lab that some of them are related to particle physics, some of them are just general physics demonstrations. That's been very popular. And I'm working on a more involved opportunity where I'm hoping to build a particle detector with the Dust Level engineering again. So that was much more involved in the sense that we have to build some prototypes and then figure out some instructions that high school students can build. But that's also something that I'm working on. I'm also, because I'm in a teaching college, I have undergraduate students. I'm working with those students to get them into the kind of work that I described today. And you don't necessarily know how to do that without some training. So, and we don't cover many of these things in classes. So I've been working on training that allows students to start working in high energy physics, even while they're undergraduate students. One of the ways I've been doing that is actually by working with graduate students from other institutions. So I run one of the programs for training my experiment, particularly focused for the US, where we run a 3-day workshop with all of the skills you need to do a data analysis project and publish a paper. That is hosted by Stanford National Lab, or SLAC, and funded by the US Atlas group. It's mainly targeted for graduate students, but every year I bring undergraduates too. So kind of a unique opportunity because I'm going there anyway. I bring Westmont students with me, and it's been very useful for them. So in conclusion, I told you about the standard model, the LHC and Atlas. I told you about why we should look for decays of the Higgs boson that are non-standard model, something exciting, something new. Maybe it solves dark matter. I told you a few examples of how, and then some things that I'm excited to do for the future, moving forward for the next 20 years, and how targeting this trigger system and high-speed electronics is the way that I'm doing that. So I think I'll stop there and hope that you have questions.
Have questions from the room, or if you're on the Zoom, you can unmute yourself or raise the hand in the thing. Robert, you have a question?
Oh, yeah, thank you for a wonderful presentation. I have kind of an odd question. Is there any possibility of using muons instead of protons?
Yes, good question. That is a, okay, maybe a dedicated slide on it, but yeah, so we want to build a collider that would allow us to look for all kinds of different things in the future. One of the things is that we want to study the Higgs boson very well, but we also want to be open or able to look for all kinds of new particles. They might be very heavy, they might not be heavy, but a muon is a great way to do it. The reason is that if you go back to that slide on synchrotron radiation, it was like 1 over n to the 4th. And the radiation, yeah, so the power radiated into photons by synchrotron radiation goes like 1 over n to the 4th. The electron is very light. The muon is roughly 200 times heavier. So if you can use a muon, you can have much less power loss due to synchrotron radiation. So on the other hand, the next slide, the muon is a fundamental particle. So you can know exactly how much momentum went into the collision. And so a muon is like the obvious particle to collide. And I think it's one of the most likely, well, I hope, I shouldn't say anything. I hope that we will build a muon collider in the next 20 to 30 years, essentially, after the LHC era. But it would be a great particle to build. It's very hard to do for some technical reasons, including the fact that the muon decays. But long answer to your question, yes, we should build a muon collider. Yeah.
So it's not possible to modify the LHC to do that. Like you couldn't just set up a new generator of muons and feed it into that, huh?
No, it's a totally different kind of collider. And there are some technological hurdles which have to do with how you get the muons into the beam. It's called cooling. And once they're relativistic, their relativistic lifetime is long enough that you can keep them in the beam. But the process of making a beam of muons is very challenging. Part of accelerator physics. Yeah.
Why is the equation for a boson M0 equals M0 plus or minus 0?
Not sure well, can you expand on your
Why
question?
isn't the equation for the Higgs boson M0
Yeah,
equals M0 plus or minus 0?
and 0 being
Nothing there.
zero.
That's a much deeper question because it does involve theory of relativity and involve general theory of relativity. I need a blackboard to go through the equations, but they're basically rested on 3 fundamental questions, maybe 4. The first fundamental question is Fermat's last theorem and its proof. Not by Wild. I have a 5-line proof of it. Okay. Again, I can do that on the paper if you want to see it. I mean, I'm happy to do it. The second one is a proof of Goldbach's theorem. Every even number is the sum of two for primes, which is related to Gödel's incompleteness theorem. Okay.
Okay.
The third one is Russell's paradox. Have you ever heard of Russell's paradox? Russell's paradox is a barber in a village shaves all those and only those that don't shave themselves. Does the barber shave himself?
Maybe we can take that one offline. We have other questions?
Do they?
Maybe we can take this offline because it's kind of
Well,
complicated.
yeah, I'm just pointing out, what I want to stress is this is also related to Hawking's view that time is imaginary and that entropy is related to area. Okay. And that's all related to this. So if you like, I'm happy to go wait for you after here, and I'll go through some of the equations if you like, because all of this is equations. It's pointed out why SU2 has no trace except for sigma 3, which is 1 and -1, but everything else has 0. And the electromagnetic field stressor has a trace of 0 identically. The covariant form of it. Okay, has a trace of 0. Okay,
I
now,
feel like I can't.
that requires some explanation,
Yeah.
and I'm happy to go through it with you. I've been struggling with this since I retired. I worked for General Research at Santa Barbara Research in the research department. I have a long and intricate history in other ways, but anyway, when I started, I started deciding that I was going to understand theory of relativity once and for all, because it didn't make any sense to me. And my first paper I sent to my former boss at General Research, who taught relativity for UTSB. And he said I was probably right, but he had a problem about scalars. Well, yeah, I mean, that's true. That's the reason. Basically, it boils down to the fact that the Pythagorean theorem is wrong.
You do this later,
Okay.
after.
Now, the Pythagorean theorem is wrong. And again, I'm not, it may sound mad, but I can point it. I can prove it in 2 lines.
Okay.
Hijack, do that after.
Somebody else have a question? You had a question.
Well, that's the reason I came here, was to try to talk to someone that had some background in theoretical physics.
Okay, later,
Okay.
later.
Using.
And if you have, I'm happy to be.
Did your
proven wrong.
hijack-
I'm delighted to be.
It's the next person's turn, sir.
Somebody else's turn.
On your untrained AI algorithms that you're mentioning.
Yes.
About how many dimensions are you using?
Right, great. So it's trained, but it's unsupervised. I didn't explain it because I was getting close to the end. So
Yeah.
the idea is that, the first example I showed, you know exactly what signal is, what background is. Here we're doing something just with the background, which is totally different than how we normally trigger. And so in the examples we've done, we have like half a dozen inputs.
Oh, okay, all right.
So it's very, very small.
Yeah, that's what I figured, yeah.
And the point is we can put that into the FPGA for the
Yeah.
high-speed electronics. But in principle, if you can fit it into the FPGA, it could be so much bigger.
Yeah.
It's hard to make things fit, but
Yeah.
that's the idea.
Can you tell us anything about what it's like to work at CERN?
Yeah.
Do you go there for a week at a time or a year or?
Yeah, so at the moment I go there for like 2 weeks at a time. I lived there for a long time before starting the faculty position here, but yeah, it's great. I mean, I really think it's a tremendous kind of opportunity for collaboration, and there's 3,000 people on the experiment because you need it. Yeah,
I mean, what's your example of a typical day for you?
typical day. Yeah, it kind of depends on the phase, but during the summers, especially during data collection, if you're involved in that, usually there's something about data collection. So you might go to the meeting in the morning for, even if you're not on shift, you might see what's happening. And then you might come back for a couple hours and in the morning work on your data analysis project, or work on an algorithm development. And then in the afternoon, say between 3 and 7, you might have a couple of meetings to present your results. So that would be fairly typical, something like that. And I try to have students do all of those kinds of things as well. Yeah.
How often is Collider actually running
Roughly from April till December.
in
And
terms of a duty cycle? It's on all the time?
well, almost.
Really?
So it takes some time to fill the beams into the collider. So there might be some times when it's not, when there's downtime. And there's some scheduled technical stops as well, but in as much as possible, it's on. So there's 24-hour shifts.
But it's not pulsed.
Well, there's bunches. So
Oh,
in a way it's pulsed. It's not a continuous beam. So there's bunches of protons. So it's basically
Yeah, that's what it was, 6 hertz, I thought.
40 megahertz.
Oh, okay. It's completely different.
Yeah. That's what makes it hard.
So with 3,000 people working on this, how do you manage time and schedules and who gets to work at when and so?
Yeah, it's basically is basically like a organization into subgroups. And so most people are involved in multiple, I don't know if that slide is, but most people are involved in multiple subgroups. So let's say I was doing something for the operation of the experiment. That's like one piece of the experiment, and that's usually organized by subdetector. So you work on a subdetector for the experiment that might have 100 people in it, and you work with 10. Then one of the other areas of organization is the data analysis, and those you always use the whole experiment. So it's not an analysis that uses one piece of the experiment. You have to stitch them all together, and so that's done in a different group of people. And there you might have a couple of hundred people in a group looking for, exotic Higgs decays, and you work with, and then that's split into like some other organizational scheme, like how those decay. And then we work with, say, 5 or 10 specific channel. So it's broken down into a way that isn't overwhelming, but for the kind of outside perspective, like, wow, we need all of these people, but somehow it would be incredibly overwhelming to work with all of them at the same time. Yeah.
What's the relative time of data generation versus data analysis?
Right. So it totally depends on what you're doing and when. So in 2010, it was extremely short because we just had no data. And so anything you could do was really interesting. And the turnaround there was probably like a month, maybe 2 weeks. Now it's getting much longer. And part of the reason is that we have a big data set already. Right. So sure, it takes time to process the data. We can solve those things. The bigger issue is just that chances are something has already been said about what you're trying to look for. And so you really have to like wait until you've doubled the amount of data, not just added 10% or something like that. So now it's becoming years. Now I could go process the whole data set or the piece of it that I want in a week or two, but I would wait much longer before I can be able to say something really new.
Are they open to public? Are there any way that just any individual can look at?
So yes and no. The full data set is not public. It's different than astronomy, and our data sets have issues in them. So there's like, and you also have to have a simulation of the detector to understand the data set. So we don't have the full data set that's public, but we do have pieces of it that are very sort of simplified. So I give students exercises on public data sets where it's like, find this particle, you can find the Higgs boson. Right. So we have pieces of it that are public. We even have a website that lets you like use a web tool where you can like make histogram in the web display. So little bits of it are.
What kind of feedback do you get from your undergraduates on their experiences of being involved?
So they really like, they're just very excited about part of it because it's something that they can get involved in, and maybe they, I would also say like in terms of like bringing students in to study physics, it's a small college, but it's attracting people to study physics, which is great.
There's a lot going on in making better magnets, with the superconductivity.
Yes.
And so on. Would it be possible, is any of that going to help you improve if you can improve the magnet by 10, for example, you might get better experiments.
I sure hope so. I mean, yeah, so thinking again, long term, one of the experiments is the Hadron Collider. The other one is this collider here, 100-kilometer collider between the electrons and then protons. It's roughly 3 times the size of the LHC in circumference. And so this experiment would have some improvement in magnet technology, but it's actually not an order of magnitude. If we had an order of magnitude magnet technology for protons, that would be very significant.
Well, with the superconductivity, they're getting higher temperatures and so on that you could build it without the same mechanics. And
yeah,
I mean, the problem might be refrigeration or something that we've known about for a long time. Just because you don't have an element that'll run at the colder temperature and the hotter temperatures. But they're making big advances I'm reading about. Of course, was it 100 years between inventing the thermometer and using it, so maybe
Right.
it takes a little while to implement this.
Yeah, I think at the moment, again, I'm not an accelerator physicist, but my impression is that most of our concrete plans of what we can do with like for sure technology we have now or like small changes to it are not that kind of development in magnet technology. But if we did have it, it might be that, you know, the kind of vision we have now is too small. Like maybe we could do much, much more.
Yeah.
In protons, for instance.
Questions? Any questions from the Zoom? Okay, great. Thank you very much.